Okay, next up in this chapter, we're going to continue looking at Lewis structures, but we're going to look at some different parts or functions of them. When we draw our Lewis structures, sometimes we're able to draw more than one for a given compound. And when that's the case, there's usually one that is drawn more correctly than the other. And there's two concepts that we look at in order to determine which Lewis structure is the best one. And those two concepts are resonance and formal charge. Resonance is when we have two or more valid Lewis structures that can be drawn for the same compound. So if we were to look at them, they follow the octet rule and all the rules they assign with drawing Lewis structures. Formal charge is a way for us to look at the electrons in our Lewis structure. And I'll get into that in a little bit, but let's start with resonance. Okay, so resonance again is when I can draw two or more Lewis structures for a given compound, and they are basically the same. Their bonds are just going to be different. And what I mean by that is if we look down here we have ozone. Ozone is O3, so there's three oxygens bonded together. I can draw that like this here, where I have for this oxygen and this oxygen, there's a double bond and a single bond here. But I can also draw it like this, where the double bond's actually on this side. Both of these are correct, but they actually exist as what we call hybrid, and they both exist. So these electrons that make the double bond, so let's say we're just talking about this one and this one that make this bond, they're either going to be present on this side or they're going to be present on the other side. But what we say is there's actually a combination of both, and we call that a resonance hybrid. To give you an example of that, you guys have all seen hybrid dogs like the Labradoodle, but here, if I were to take two purebred dogs that are different breeds and I breed them together, I get a hybrid dog. So it's a combination of both. The same thing is true with our resonance structures. So here I have the ozone, where we have the double bond on this side, the double bond on that side. It actually exists as both. And these dashed lines right here represent the two electrons that make up the double bond. And what they're doing is they're going from one side to the other. So it's an intermediate between the two. Okay, so we're going to draw the Lewis structure for the nitrate ion, and we're going to include any resonance structures. So we're going to do this like we normally do. Let's countervalence electrons. For nitrogen, it's 5. Okay. Oxygen has 6 valence electrons. 6 times 3 is 18. Okay. And then I have a -1 charge, so I have one more. So I have 18 plus 6, so I have a total of 24 electrons. Okay. My central atom here is going to be nitrogen. So you're going to have oxygens on each side of that nitrogen. First rule is we're going to fill the octets of our outer atoms. So 1, 2, 3, 4, 5, 6. So we're going to go ahead and draw those two as a line. Same with these. We'll put our 8 around each one of our oxygens. Okay. So I put 8 around our surrounding atoms. How many have I used total? I've used all 24 electrons. So now I look at my central atom. Does my central atom have 8? It does not. It only has 6, so I need it to have 8, so I'm going to make a multiple bond. So I'm going to grab, I'll grab this one. Okay, and if I do that, I get a double bond here. This stays a single bond. This stays a single bond. I still have my 8 electrons around. This one now has 2 here and 2 here. So now there's 8 electrons around there, around our nitrogen. So that's correct. Okay. Now, here, who's to say that I had to pull from this oxygen? Could I have pulled for this one? Sure, I could have. I could have also pulled these two instead and gone here. And if that was the case, then my double bond would be here. Okay, so that is, even though it's basically the same structure, it's not because the double bonds between two different atoms that you saw here. Now the same is true here. I could have pulled from here and put those there. So then I have a third option here. The double bond could have been here. So I had three options for my Lewis structure here. And these are all resonance structures of each other. We show the resonance with a double arrow, showing that these interchange. So the nitrate ion has three resonance structures. So let's do it for nitrite. Nitrite, again, let's start here. We have 5 valence electrons. Oxygen has 6. 6 times 2 is 12. So it gives me 17 plus 1. I have 18 valence electrons. So here I'm going to go ahead and put my 2 there. Let's put 8 around each of our surrounding atoms. So 2, 4, 6, 8, 2, 4, 6, 8. I've used 16, so I have 2 left. I'm going to put those 2 on the central atom. Is my central atom satisfied? The answer is no, it only has 6, so I need to make a multiple bond. So I could either choose from here, or I can choose from this oxygen. So I actually have, if I chose from this oxygen, there's going to be a double bond here. Oops, I have to draw the line. Okay. Or I could have chosen it from the other side. So the nitrite ion has 2 resonance structures. Here are some simple rules for resonance structures. Resonance structures must have the same connectivity. That means that the atoms are going to be in the same place. So you're not going to rotate atoms. And what I mean by that is, let's say I have a nitrogen bonded to an oxygen, and this one's bonded to a, I don't know, let's just say a carbon. The resonance structures have to have the order of these. So you can't switch them like this. So switching those 2 atoms and how they're connected, that would not be a resonance structure to this. So it's only the electrons that are changing position. Resonance structures, if they are resonance structures, they should have the same number of valence electrons. We know that second row elements have a maximum of 8 electrons. The third row and above can have an expanded octet. And then when we start looking at formal charges must be the total, or the total must be the same for each resonance structure. Now, a couple things about resonance structures. When we're looking at formal charge, the fewer formal charges we have, the better the structure is. The smaller the formal charge we have, the better the structure is. And if we're looking at competing structures, if there's negative charge, the negative should be on the more electronegative atom to be a better structure. So let's talk about formal charge. All right, formal charge is a way of us looking at valence electrons and bonding electrons and non-bonding electrons, and it gives us an idea in order to distinguish which of our competing structures is better. In general, here are the rules. The sum of all formal charges in a neutral atom must be 0. The sum of all formal charges in an ion must be equal to the charge of the ion. Small or 0 formal charges on individual atoms are the best. When formal charge cannot be avoided, negative formal charge should be on the most electronegative atom. This is how we determine formal charge. Here is your formula. So go ahead and write this down. So you got the number of valence electrons, like for fluorine it would be 7. And then you're going to subtract from there the number of non-bonding electrons plus half of the bonding electrons. Okay, so let's look at an example for HF. Here is our Lewis structure for that. So I want to calculate the formal charge of, let's start with fluorine. Fluorine has 7 valence electrons. It's in group 7. Okay. Now, the number of non-bonding electrons in fluorine is 1, 2, 3, 4, 5, 6. There are lone pairs. I have 6 of them. So 6 plus half the number of bonding electrons. It's a single bond, so there's 2 bonding electrons. So half of that is 1. Okay? So 7 minus 7 is 0. So the formal charge of fluorine here is 0. Hydrogen has 1 valence electron. It has 0 non-bonding electrons. It doesn't have any lone pairs. It has 2 bonding electrons associated with it, these 2. So half of 2 is 1. And so 1 minus 1 is 0. So our formal charge for hydrogen right here is 0. And that's a good thing. We want it to be 0. Okay, let's look at another one. This one we're going to look at sulfur dioxide. So let's look here. I'm going to take you through each one of them. Let's start with this oxygen. Oxygen has 6 valence electrons, right? So I'm going to subtract that from how many non-bonding electrons do we have? So this should kind of be in brackets. Anyway, we have 1, 2, 3, 4. So it's 4 minus half of the bonding. So how many bonding? 2, 4. So half of that is 2. Okay. So we have 6 minus half the bonding is 2. So I have 2, 4, so half of it is 2. Then I'm going to add those 2 together. Sorry, I put minus here and it should be plus. Confused myself. And so I get 0 as my formal charge for that oxygen. So let's look at sulfur here. Sulfur is in group 6. There's 6 valence electrons. It has 2 non-bonding. Sorry about that. Glitched. Okay. Plus half the bonding. So the bonding is 2, 4, 6. So half of it is 3. So that equals a positive 1. So sulfur here has a positive 1 formal charge. Oxygen here, we're going to have 6 minus our non-bonding is 2, 4, 6. So 6 plus, I have 2 bonding, so half of that is 1. So that's going to be negative 1. Negative 1. Okay, so that's a formal charge for each one of those. Now, it should add up, all your formal charge should add up to be the charge of your molecule. Well, here, my molecule is neutral, so the overall charge is 0. So this should add up to be 0, and it does. All right, drawing resonance structures and formal charge. So we're going to look at a couple different examples here. All right, when we do this, this is what we want to do first. Draw the Lewis structure that maximizes the octets, assign formal charges, then you're going to move electrons, so this is where you're going to do your resonance, and then from there we can figure out which one is the best. So let's actually look at an example. Here are 3 resonance structures for the cyanate ion. Right? They're already drawn for you. All 3 of them exist, but that doesn't mean they all 3 contribute the same way. And what I mean by that is, remember when we talked about resonance, they both exist because the electrons are moving from one side to the other, if you think about ozone. But it doesn't always mean that one is it's going to be, if I have 2 of them, it's going to be 50-50. Or in this case, if I have 3 of them, it's going to be 33% each. One of them may contribute more than the other, and the way we figure that out is by the formal charge. So let's look at formal charge here. So oxygen has 6 valence electrons. Here it has 6 non-bonding plus 1, half the bonding. So 6 minus 7, this has a formal charge of -1. Carbon has 4 valence electrons. In this case, there's no non-bonding, no lone pairs. And then half of the bonding, 2, 4, 6, 8, half is 4. So 4 minus 4 is 0. Nitrogen here, 5 valence electrons. It has 2 non-bonding. And then it has 2, 4, 6 bonding, so half of that is 3. So 5 minus 5 is 0. Okay. Carbon for all of these is going to be 0. You can see there's 4 bonds, so that's not going to change. Let's look at oxygen here. I have 6 minus, I have 4 non-bonding, 4 bonding, so half of that is 2. So I have a formal charge of 0. Nitrogen here, 5 valence electrons, 4 non-bonding, 4 bonding, half of that is 2. So I have an overall charge of -1. All right, oxygen here, 6 minus 2 non-bonding plus 2, 4, 6 bonding, half of that is 3. So 6 minus 5 is +1. Okay. Nitrogen here is going to be 5 valence electrons, 6 non-bonding, plus half the bonding, which will be 1. So 5 minus 7 is -2. Okay, now one thing I want to point out is that the cyanate ion overall has a charge of -1. So all your formal charge should add up to be -1. And in each case it does. So that's good. Now we want to look at which one is our best contributor. Now we're going to do that by looking at where the formal charge is. First of all, we want the least amount of formal charge. So this one's going to be out automatically. Because it has formal charge that is not 0 on 2 different ones, and it also has a bigger number than the rest. So that's definitely not going to be our biggest contributor. Now we're going to look at these two, and the difference is we have a -1 on nitrogen and -1 on oxygen. So we want to look which one is more electronegative. Oxygen is more electronegative. So that means we want the -1 to be on the oxygen. So A is going to be our biggest contributor. Okay. All right, let's look at one more. Here we have dinitrogen monoxide, and we want to figure out which one of these resonance structures is the highest contributor. So I'm going to give you a second. Go ahead and pause this and go ahead and write your formal charges. Okay, so remember nitrogen has 5 valence electrons. So here we have 5 minus 1, 2, 3, 4, 5, 6. So I have a -1 charge. This is going to be 5 minus 4, which is a +1. This will be 6 minus 6. So this will be 0. Here we go. We have 5 minus 5, which is 0. This one's going to be +1. And this one's going to be -1. All right. Here I have 5 minus 6 plus 1, which is 7. So this is going to be a -2. This one will be 0. And this one will be a +2. Okay. So automatically this one has the highest formal charge. That's not going to be our biggest contributor. Here I have negative charge on my nitrogen, negative charge on my oxygen. The nitrogens in the middle are the same. They're both positively charged. Where should the negative charge lie? It should lie on the more electronegative atom. So B is going to be our biggest contributor. Okay. All right, that takes us through formal charge and resonance structures.